Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to build off of the local max and min work we did last time and talk about absolute max and min problems. So this is kind of related to that really famous Calc 1 result called the Extreme Value Theorem. So the two most important conditions of the Extreme Value Theorem are that one, the curve was closed. Well, I should say appears on a closed interval. So we basically had like f of x on some, typically use like a and b closed interval. And the other thing was that the function needed to be continuous. And this picture is basically summing up what I'm saying. So it was saying that if we have those two things happen, then the curve will somewhere have an absolute, like have a highest value and a lowest value. Now, those values may also be found using local max and min techniques, but you could also just take something like, a line like this, right? Like that. And it has no local max or min, but it has an absolute minimum over here at this endpoint and an absolute max over here at this endpoint. So if you have these two things, then you'll always get what we can call an absolute max or min. And that's last year's stuff, okay? And like a lot of things in Calc 3, basically we're just going to build on that notion, bump everything up a dimension. So what we need to work with are what we call closed sets. Really, they're like called compact sets like this. This is a term from actually the kind of area of math that I used to study a ton of called topology. But really simply, just like you have a closed interval from A to B here, we don't want open, two-dimensional spaces like an open disk or something. We want a closed circle or something like that. And basically we don't want any weird undefined things in there. So we want nice closed, sets, which really we can call compact sets. So down here is basically what our extreme value theorem will be. So it says a continuous function f of xy on a closed and bounded set D, so that's this thing, right, in the plane attains an absolute max value at some point of D and an absolute min value at some point of D. So basically just saying like if you, drew like, you could take something like this, right? And if you have like a paraboloid, right? So you have like that thing, and you've got this. You could, think of a paraboloid as over some closed, like rectangular space. And I'm just doing dotted in the back because it was behind it. So here we can do it this way. So imagine this is, above the like space in the this is in the two-dimensional plane XY down there. So somewhere if you go up and this thing, the way it grows, right, there's going to be like an absolute max value, right? I mean, actually it would be the same everywhere because of the shape it is. But there's going to be an absolute max value of it. And there's definitely a min value down there, which we could find using like local max min tricks. So this is an absolute and also, a local min. And then like up there on like that top level would be like an absolute max. Not a local max because, really the function keeps going up and up and up. It's only absolute max because of the bounded, the closed disk or square in the XY plane. So kind of a lot of things to check, and honestly probably just best to go through an example here. So basically this is how I think of these problems. Two parts. So first, so we have like some sort of function here, right? And this is so this actually is like a rectangular region, kind of like that example I was talking about. So we're first going to verify that the function is continuous on the closed set. Then we're going to find all the critical points for f and determine if that point is a local max or min. Then we'll check for max min values on what they're calling D is the boundary. So basically checking on the edge of the disk. So again, you got to think of the surface being mapped above this. And maybe when it gets mapped above this, there attains a max or min value, local or absolute, honestly, on the edge of this thing. So so this is continuous everywhere. There's no dividing by x or natural log or anything weird. So it's definitely continuous. It's on a closed set. So we're going to just jump into finding critical points. So find your partial derivatives. In this case, you get 2x minus 2y. And then f with respect to y is minus 2x plus 2. Here, this is going to basically reduce and say that y has to equal x, right, if it needs to equal 0. And then likewise, here if we set it equal to 0, so I guess I should say set equal to 0, then we would get x is, 1, right? And so now if you sub that in here, it's saying that, y also equals 1. So the point 1, 1 is a critical point, and if you plug in 1, 1 to the function, you'll get 1, okay? So we're going to I'm going to circle that, I think, in purple here. So this is a contender, right, for the absolute max or min value of the function, because the local max or min could be an absolute max or min, just like we were talking about down here. This point was a local min that also, we could have found with what we just did, and it would turn out to be the absolute min also. So now we have to go through and check max min values on the boundary, okay? And I think I'm going to just start, I'm going to try to organize this in kind of colors here. So we're going to check on this, I'm going to call it line 1, okay? So that line is the line y equals 0, right? So the function would reduce to x comma 0, and that means that this thing up here just becomes x squared, right? And we see that the lowest x value is 0 and the highest one is 3, and so it's not too hard to see that basically we get a min at 0, 0, right, of 0, and a max at 3, well, I guess I should say it like this. So a min at x equals 0 of 0, and a max at x equals 3 of 9. There you go. Okay, so that is, kind of two more contenders for mins and maxes, absolute min and maxes, right? Then let's do, so line 2. All right, so line 2 over here, basically we're just reducing it based on that condition, and that condition there is basically that x equals 3, right? Let me do that parenthesis thing up here. So then we would have, instead of x comma y for the function, we'd have 3 comma y, right? And if you plug in 3 comma y, you're going to get 9 minus 6y plus 2y, or, this simplifies to 9 minus 4y, all right? And 9 minus 4y is just a linear function, and the possible y values are either 0 or 3, right? And I feel like I just said the wrong thing. I think I said 3. So the y values are 0 or 2, right? And if you take away nothing, then it's going to have its max value. And if you take away 4 times 2, then it'll have its min value. So here we're basically getting min at y equals 2 of 1, right? 9 minus 8, yes, 1. And then you're going to get a max at y equals 0 of 9, okay? So now we have 2 more contenders, basically. So far, just kind of to recap, all we've checked are this line, and then inside, right, in there, which is we did with this part up here. And so far we have a absolute min of 0 at 0, and we have a absolute max at 3, and also 3 and x of 9, and y equals 0 equals 9. So basically now we're just going to go ahead and keep moving along. And I think, if I planned this well, yes. So I kind of had a feeling this would take up 2 slides. So we're going to do the same kind of thing, but now for, what colors did I use there? We'll go on this line up here. So on line 3 here, basically y is 2. So we have f of x comma 2, which is going to reduce to, that'll reduce to x squared minus 4x plus 4. And that is a quadratic that factors nicely. It's a perfect square, right? And honestly, to optimize that, I would just think of the graph of the quadratic. It's in vertex form, shifted over 2, just kind of looks like that, right? And so that's in general what it looks like, right? And we are graphing between x equals 0 and x equals 3, right? And you can see, it has its minimum like at 2, right? So let's put that down. So it has a min at x equals 2 of 0. And then it would have a max, so if we're over here at 3, right? So the only regions that we can kind of graph between are really right here and here, right? So, because 3 is the most. And since we can go further this way, we can get higher up. So here we wouldn't get as high, right? So if we plug in 0, we would get 4. So it has a max at x equals 0 of 4. So these are now 2 more contenders that we have, right? And we're just going to do the last one. So line 4. So on line 4, basically here, we have that x equals 0. So we simplified to 0 comma y, which would be just the function 2y, right? And in terms of y values, right, it's a nice increasing linear function. It's going to have its max at the highest y and its min at the lowest y. So here it has a max at y equals, what was it, 2 of 4, and a min at y equals 0 of 0. So, my last two contenders. So, the question was find all absolute max and min values, or find the absolute max and min values of the function. And we never got below 0. Oh, I thought I had this thing on. We never got below 0, right? We got it a few times, here. And we never get above 9. So basically the max value is 9 and the min is 0. It didn't ask, I think, where, but we basically found it, right? So it's like a min at x equals 2 of 0. This is actually a graph of what it looks like. So these are minimum values, and then it's like maximum values and stuff. So that kind of sums it up. Lot of algebra, but this is, honestly the only way you really can do it. It's a lot more difficult than, when you do the extreme value theorem last year. You just literally plug in this number and you plug in this number and you check the, height, in a sense, of the function, of the curve. But here, we're still doing that, but it's just way more work. A lot of times when we plug in, some sort of condition on that, slice or whatever, we get some sort of new two-dimensional thing that then we have to maximize. And sometimes even that thing can be hard to maximize. So we might even use the derivative of this to help maximize it, right? We could take the derivative to, figure out a maximizing, minimizing sort of trick there. But yeah, I think that is all I want to say. Basically, check interior critical points. Local max or min could happen in there, and those could be global max or min. And then you have to go through this boundary thing and check along the boundary for any other possible max or min.